Page 70. And the two chemicals that we have are potassium iodide, Ki, and it is you guys can take a look at this. What state is this potassium iodide? Is it solid? No, it is not solid. Is it gas? No, it is not gas. Okay, so we've eliminated solid, we've eliminated gas. Is this potassium iodide liquid? Did we melt it? If we didn't melt it, it is not liquid. Okay, liquid is when you melt it. So this is not liquid, it is aqueous. Okay, so we're going to put a little AQ down here. This is the one where the states are important. Okay, this is in our double replacement reactions. The states are important. Okay, so we have Ki. We have Pb. NO3, and if anybody just came in and did not get a blue sheet, come grab a blue sheet off the front desk here, please. Okay. So here's our lead nitrate. What state is the lead nitrate? Is it a solid? No. Is it a gas? Brooklyn, is it a gas? No. Am I being weird? Yes, I know. Is it liquid? No. If it was liquid, I would have had to have melted the salt. In order to melt a salt, you have to heat it to about 900 degrees Celsius. Have I heated anything to 900 degrees Celsius here? No. So this must be aqueous. So this is also aqueous. So our double replacement reactions, the states are always important, and it's always going to be aqueous plus aqueous. Those are your reactants. Your reactants are always going to be aqueous plus aqueous. And I'm going to stand up here so you guys can see a little bit better. Okay. And you have to pay attention because if you blink, you will literally miss it. This is a very fast reaction. Okay, are we ready for these two things to be mixed together? Okay, here we go. 5, 4, 3, 2. Whoa. It used to be transparent, right? Both solutions were transparent. Is it transparent anymore? Not transparent. I want you to think about that. What is making it non-transparent? We dealt with this back way at the beginning of the semester when we did that lab where we, it was transparent and then it was cloudy, right? And then you filtered it and it was transparent again. What makes something opaque or cloudy? Have a think about that. Yes. It is a suspension. And if it is a suspension, what is suspended in the liquid? Little solid particles, little tiny solid particles are suspended in the liquid. And in fact, I did this. Oh, did they go missing? Oh no. Oh no, here it is. I did this last week. And you can actually see it has settled over time, right? Some of it has gotten stuck to the sides, but do you see how a lot of the solid has settled to the bottom? Okay. So that is a suspension. So what that means is one of our products has to be a solid. Okay? So we have Ki, PbNO3. And what we're going to do is we are going to, this is a double replacement reaction. We are going to take our outside ions. So this is an outside ion. And that's an outside ion. And we're going to combine them. So we'll take our outside ions and we're going to combine them. So what is the charge of K? Plus. Okay. What is the charge of NO3? Minus. So I don't quite have enough room to do it here, so I'm going to show my products down here. Okay, so we have now K NO3. Yeah? And now that you have a blue sheet, you can tell me, is that KNO3 going to be aqueous or is it going to be solid? It's going to be aqueous. Right? Because all nitrates are soluble, all nitrate salts, all alkali salts are soluble. So we have both an alkali, the K, and we have nitrate, so it is soluble, which means that it is aqueous. Now our other product, we combined our outside ions. Now we're going to combine our inside ions, and we're going to go backwards. So we're going to start at the lead and go to the iodine. So we're going to combine our inside ions. So for the outside ions, you go forward. For the inside ions, you go backward. The reason that you do it that way is to make sure you always write your metal first. Okay? If you do it that way, you'll always write the metal first. So go outside ions, go forwards. Inside ions go backwards. So now we have Pb, and then it ends up going with I. Pb, what is the charge of lead in the lead nitrate? 2+, because we've got 2 NO3-, so that's 2+. And iodide is -1. So what is the formula of our other product? Formula of our other product is PbI2, yes. PbI2. And if you guys wouldn't mind too much, could you go look on your solubility table and tell me, is PbI2 solid or aqueous? So remember, you look up the anion, so you're going to be looking up the I. Okay, so you say, I've got I look up my anion, and then it's going with lead. And if it's with lead, it is low solubility. And what does it mean if it's low solubility? That means it is the solid. Okay. So this is solid. And this right here is called, it forms a yellow precipitate. So the precipitate is the solid that forms during a double replacement reaction. Okay, so it's going to be a solid salt. It's going to be an insoluble salt, a low solubility salt. So the precipitate if we go up here and we define the term precipitate, it is a precipitate. And I'm going to show you, because that's a long word and we write it a lot of the time, you can abbreviate it as PPT. Okay, precipitate is PPT. And the precipitate is the low solubility salt that forms a solid in a double replacement reaction. Am I going to have you define that? No. But you should be able to recognize it in context and understand what it means, so that, you know, if I say, what is the precipitate in this reaction, you know what I'm talking about. Does that make sense? Okay. How did we know that a precipitate formed when I put those two reactants together? What did we see? What happened to this visually? The liquid started out clear. And what happened after the reaction? Yes. We got a color change, but it could have changed color and just been like clear yellow, right? Would have looked a lot like pee or something. It's not very nice. What else do we know about this? What else happened? Yeah, it went opaque, okay? So either it's going to go cloudy if you get a small amount of precipitate, or it's going to go opaque if you get a large amount of precipitate. So it turns cloudy if there's a small amount of precipitate. It turns opaque if there's a large amount of precipitate. Some precipitates will be clumpy. Some will be fluffy, almost. They'll look a little bit fluffy. So there's different qualities to the precipitate, but it'll always look somewhat cloudy or somewhat opaque. Okay, you'll always see that solid. Okay, and the reason they are cloudy and opaque is because the solid particles formed scatter the light. And if we have those solid particles, we have a suspension. So our reactants were two different solutions. We poured them together and we got a suspension. Okay. So now what we're going to do is we're going to look at the picture on the next page, because this is going to show us what happens on a particle level. Okay? So here we have our sodium nitrate. This is an NaNO3 solution. And you'll notice that in the solution, the ions are separate. Okay, and over here we have a K2S solution, and you'll notice that the ions are separate. Although these ions look gigantic in the picture, they are actually super. Okay, ions are teeny tiny. Are they big enough to scatter light? No. Do you remember the solutions we saw at the beginning? Light just went right through. Individual ions are too small to scatter light. So this solution here is going to be clear. The other solution also has individual ions which are too small to scatter the light, so it is also going to be clear. So we have a clear solution, we have a clear solution. Solutions are always clear, right? Because they've always got all the ions are individual, so they're all too small to scatter the light. So we're going to put these two together and mix them. And actually, before I show the picture, could you guys, let's just take a look at our reactants here. Let's take our outside ions. So I have Na and I have S. What is the formula formed by Na and S? Na2S, because S has a 2- charge, N has a +1 charge, so we need 2 Nas. And then, so those are our outside ions. And then we're going to do our inside ions. Which direction do we go for our inside ions? K comes first, and then NO3 comes second. K is positive, NO3 is minus, so we'll end up with KNO3. So if we look, those are inside ions, sorry. Ions. If we look over here, and I mix them together, if you go and you look up NaS, let's go look up NaS. Here's sulfide. Here's sodium. Sulfide plus sodium is soluble. So that means it's aqueous. And if it's aqueous, that means it's a solution. And if it's a solution, it is clear. Okay. KNO3, I don't even need to look that one up because what kind of a metal is K? What kind of metal is K? Alkali metal. And alkali metals are soluble with everything. In fact, over here, Na is also an alkali metal, so it's soluble with everything. NO3, nitrate, is also soluble with, and I don't have room to write everything, so I'm just going to write all, okay? So nitrate soluble with all, potassium soluble with all, so it's still aqueous. So if we look at this, has any solid formed here? No solid forms. Is this going to be clear or cloudy? It's going to be clear because if there's no solid, there's nothing to scatter the light, okay? So if there's no solid, there's nothing to scatter the light. And here's the big question. Did we get any new substance? Or did we just mix things? We just mixed. There's nothing new. Everybody was floating around separately. And now they're still floating around separately. All the ions still floating separately. So there's no new substance. And if there's no new substance, has there been a chemical reaction? No. No reaction. NR. So if you have a case like this where both of your products are aqueous, and you will have to look them up on your blue sheet. So what you're going to do is you're going to predict the products and then look it up on the blue sheet. And then you're going to say, oh, they're both aqueous. Dang, that means there's no reaction. So what you will actually do is you will cross this out and write no reaction, because really, we didn't actually form anything new. It just stayed mixed. Okay? So for single replacement, you use the activity chart, which is on the back, by the way, of this solubility chart. So if you would like to, on your sheet, you can write on the solubility chart, this is used for double replacement. Okay, so the solubility chart is for double replacement. And then on the back, you can write that the activity series is used for single replacement. Because sometimes people get confused. They're like, which chart am I looking at? Am I looking at the activity chart? Am I looking at the solubility chart? So the activity chart is for single replacement. The solubility chart is for double replacement. And if you're finding that's too much writing, you can just write SR. And on the other side, you can write DR. Okay? There you go. All right, back to here. Now let's take a look at another example here. We have NaCl, and it is aqueous. So this is a clear, and it is a solution because it is aqueous. AgNO3 is clear, and it is a solution because it is aqueous. And all the ions are floating around. All ions float separately. Now, if you get really good at this, you don't even need to write the products before you start predicting if you're going to get a precipitate. Who do we put together first? We put the outside ions together first. You could do the inside ions first, but it's always good to do it the same way each time. That way you won't make a mistake. So we have our outside ions, NaNO3. Can anyone tell me right off the bat, what is NaNO3, soluble or insoluble? NaNO3. NaNO3, it's got an alkali, soluble. It's got a nitrate, soluble. Okay? If you start remembering that alkalis are always soluble and nitrates are always soluble, it kind of speeds up. You don't have to look it up every single time. Okay? Then we combine our inside ions. We have Ag and Cl. Go look that up on your chart and say, is Ag and Cl soluble or low solubility? AgCl. Cl and Ag. Well, we go and we look up the Cl, and we see it's with Ag. And if that's the case, it is low solubility, which makes it a solid. So that if we go over here, there is our AgCl, and that is our, what does PPT stand for? Precipitate. Have you guys heard of precipitation? Like rain falling from the sky? Well, you know what the solid does? It falls out of solution. It might take a while, right? But it eventually settles. So this precipitates out of solution. It falls out of solution, just like rain falls from the sky. Precipitation falls from the sky. The precipitate falls out of solution. Okay? And the precipitate is the solid. So what does that look like in the beaker? This time, instead of having everybody just floating around separately, this time the silver and the chloride get together and they form a solid. I have shown that solid as a single chunk. It's not really a single chunk. There's really like teeny little bits of solid here and there all over the place that are all scattering the light. But what happened with the Na and the NO3? Did anything happen? No. Okay, so the Na and the NO3 are just hanging out, letting the reaction take place. They're not participating. Okay, so we have our solid, that is our precipitate. And in this case, a reaction occurs, and you would be expected to show the aqueous and the solid as the products. Okay? There is a third possibility. We had no precipitate. We have one precipitate. What's the third choice? Two precipitates, absolutely. Okay, so we're going to look at a choice where a situation where we get two precipitates. So copper sulfate is aqueous. You can go and look these up if you want to. I have specifically picked things which are soluble, but copper sulfate is soluble. You can look it up on your chart if you want to. Strontium hydroxide is also soluble, so it is aqueous. Let us combine our outside ions. We have Cu and OH. What is the charge of Cu in CuSO4? SO4 is 2-, so that means copper is 2+. Yeah? Strontium, we can just look that one up. Strontium is 2+, and hydroxide is OH-. So now we're going to combine our outside ions, Cu and OH. So that's going to be CuOH2, don't forget your brackets. And then we'll combine the strontium with the sulfate, so that's going to be SrSO4 because they have the same charge, they balance each other out. And we get copper hydroxide, CuOH2. Let's go check CuOH2. Hydroxide with copper 2+. Where is copper 2+? I don't see it anywhere. Oh no. If I don't see it, that means it belongs in all others because it doesn't appear anywhere. So if it's in all others, then it is low solubility, which means it is a solid, which means it is the precipitate. Our other compound was strontium sulfate. So let's go find sulfate. Here's sulfate. Sulfate with strontium is also low solubility. And so that means it is also going to be a solid. So when we go and look at our products, you can see everybody has formed a precipitate. Okay, we got precipitate number 1, we got precipitate number 2. This is a solid, this is a solid. And like I said, they won't be a single like little cube at the bottom. It'll be all sprinkled out all throughout, but this is easier to show. Okay? And now there's just a bunch of examples showing how to just predict the products. Ooh, that should say BR. I need to fix that. So we have NaBr. So the way to do it is to write out all your ions. I've got Na plus and I've got Br minus. I have Pb, which because it's with NO3 2, I know that NO3 is -1, so if I have 2 NO3s, that means that Pb has to be 2+. And so there we go. And now we're going to combine our outside ions, the Na and the NO3. And then we will combine our inside ions, the Pb and the Br. Okay, so when you predict the products, split up all the ions, write them with their charges, combine the outside ions, then combine the inside ions. Okay, so we would then have outside ions give us NaNO3, inside ions give us PbBr2. So our products are PBBR2. And of course, once you have your products correctly predicted, you must balance that reaction. Okay? And don't forget, if they're both aqueous, what do you do? No reaction. Okay? Remember, if both products are aqueous, no reaction. There are a few more examples, but I think we've done lots of examples. If you want to take a look at them, feel free. There's like 3 more examples. All right, but there are some exercises here. All right, there's a little bit of space above and below, so you can write the ions. So number 1, write out the ions. 2, combine the outside ions, combine the inside ions. 3, predict the state of the products. And 4, if both products are aqueous, right, if one of the products is solid, then you're going to balance it. If neither are solid, then you're going to write no reaction. Hello, hello. We had Adrian is not here. Awesome. And Nima is. Thank you. Cool. Thank you so much. Whenever you go. All right, so you guys are going to be working on that for a little bit. Hello. Yeah. So here's the thing. We will make the concentration small after the vehicles. So yeah, if you can just put all the reactants will automatically be increased. The thing is, but this just means if it's soluble, you can make more than 1 mole, more than 0.1 mole per liter. But like, let's say like maybe 0.005 mole, I can make that. That's why it doesn't say not soluble, it says low soluble. It just means you can make it aqueous, but only a lower solution. Yes. Yes, that one. Yeah, big long one. Yeah. Yes. Is there anyone else who did not get their test back yesterday? If you did not get your test back yesterday, you can come on up and I will find it for you. Okay. Just bring it back when you're done. No. Yes. Yeah. Bring it back when you're done. Yunha, did you want to see your test? Were you here yesterday? No, but you don't want to see it? You're like, no, it's okay. Okay. Okay, and we need that quiz. For a moment. Page 76. So there's actually a few different theories of what makes something acidic. All right. Do you guys know anything about acids? Any characteristics of acids? Any properties of acids? Yeah? They have a hydrogen in it. Yep. Do you guys know what they taste like? Acids taste sour. So if you think about vinegar, vinegar is an acid, yeah? If you think about, that's acetic acid. If you think about lemon juice, that contains citric acid and ascorbic acid. So acids taste sour. Bases taste bitter. Okay, in grade 12, we'll learn a whole bunch more about the different properties. You probably learned some of them last year in grade 10, but we're not going to spend a lot of time talking about the properties this year. But the reason an acid tastes sour is because when it dissolves in water, we take our HCl which is a gas. Do you see how they're little molecules? Yeah? Okay, molecule, molecule. And acids are weird because although they are molecules, they are also, we consider them to be made of ions. So they're an unhappy blend of molecular and ionic. Okay? They make me unhappy too. So if you're like, I'm not comfortable with it being both a molecule and then dissociating into ions, that's okay. You'll just get used to it over time and then you'll feel okay about it, even though it's not particularly making sense. So what happens is the molecules dissociate. Do you guys remember what dissociate means? To dissociate means to split apart. Okay, we are on page 76, okay? So to dissociate means to split apart. So the hydrogen separates from the chloride. So now we have freely floating individual ions. Okay? And that is the definition of an acid, is it is a substance that releases hydrogen ions when dissolved in water. Okay? So an acid releases H+ ions when dissolved in water. And it is those H+ ions that interact with your taste buds. They like zip into the little taste bud and they go, ooh, sour, okay? And sometimes if you take an acid and you pour it onto a metal, it'll actually start to eat through that metal. And it is the hydrogen ion that is causing it to eat through that metal. That's actually a single replacement reaction where that hydrogen ion is replacing the metal in that reaction. So those are our acids. So what we can see here is we can write the dissociation reaction equation for the acid. We start with HCl as a gas and it dissolves into H+ and Cl-. We start with H and BrO3. That will dissociate into H+ and BrO3-. This is not the same as decomposition, okay? This is not a chemical change. This is a physical change. Because if I really wanted to, I could write H plus aqueous and Cl minus aqueous. I could just write it as HCl aqueous. So I started with HCl and I finished with HCl. Was there any actual change of substance? No. Even though the ions have separated, we still consider that just a physical change because it's just a change of state. Okay? Physical change because it is a change of state only. So dissociation is not the same as decomposition. I guess a good way to put it would be if you had the HCl and you decomposed it, it would make hydrogen gas and chlorine gas. Yeah? Whereas if you take HCl and you dissolve it, you get H plus and you get Cl minus. If you were to evaporate the water, you would get HCl back again. Okay? So that's kind of how it's different. Now, again, it just says here as although acids are molecular compounds, they still dissociate in water to form ions, which is weird, and we just need to live with that. Bases. Remember we said they taste bitter. Okay, so we've got the acids taste sour, the bases taste bitter. And that's because bases produce OH minus. So we can take our NaOH. This is the Na. This is the OH. And this is a solid. And we're going to toss it in the water. And what do we say happens to the ions? They split apart. What's the other way of saying split apart? They dissociate. Okay? The ions dissociate. In other words, they split apart. So now we went from having NaOH solid to having NaOH aqueous. Do we have the same substance at the beginning and the end? Yes, we do. No new substance. That is a physical change. So in essence, bases are just ionic compounds, but the anion is always hydroxide. Okay, and it is the OH minus ion makes bases taste sour or bitter. And if you ever have trouble remembering that, bases taste bitter. So we have acids, which release hydrogen in water. We have bases, release OH in water. And then, lastly but not leastly, we also have salts. So here is our salt, and that a salt is just an ionic compound. And the only thing is that it can't contain OH, because if it contained OH, it would be a If it contained OH, it would be a base, okay? All right, and salts, as long as they are soluble salts dissociate into free floating ions. Okay, so acids dissociate into free floating ions. Bases dissociate into free floating ions. And as long as the salt is soluble, it will dissociate into free floating ions. If it is not soluble, it'll just come together and stay as a solid. Okay, so those are acids, bases, and salts. So what you are going to do is you're going to do number one, and you're going to decide, do we have an acid, do we have a base, or do we have a salt? And the second thing you're going to do, and we're going to do the first couple together so that you get the idea of it, we're going to write the dissociation equation for each of these. So if we have, and this is on page 77, if we have HBr gas and we put it into water, it will dissociate into H ions and Br ions. What is the charge of the H ion? The H ion is +1, and the Br ion is -1. And we put a plus in between those, and both of those are going to be aqueous because it just dissolved into water. Okay, let's try KOH. So you're going to separate the two ions. There's a K ion, and there is an OH ion. What is the charge of the K ion? K is plus, OH is minus, and those are both going to be aqueous. We're going to do one more before the bell goes, because I want to show you what happens if you've got two of them. Strontium, we have strontium, and we have two hydroxides. So we have Sr, which is 2+, and we don't write OH with a little 2 down at the bottom. They float around separately, so we write it as 2OH minus. We have a 2 and a 2. So that is aqueous and aqueous. So you're going to work on pages 76, 77, I think it was. And then you're going to also do page, 77 and whatever the hell the last one was. 74, 75, and 77.